Hi, I'm Professor G.K. Srinivasan. Welcome you all to the MA106 course, Linear Algebra. This is the first half of your second semester math course, which is the second half consists of MA108. And I'll be teaching this course with Professor S. Krishnan. And I'm just showing you my video just for a few minutes. I'll be shutting my video off and I'll be projecting the slides. I hope you will enjoy your experience in IITBombay. And unfortunately, this course is online. I'd love to see you all in person, but maybe in some future we'll certainly get to meet. But until such time, enjoy this course. This is your first half of the second semester course. So let's get to the slides. So the slides have been prepared by Professor Krishnan, and here are the slides. We will also be meeting once a week for a live session, and the textbook is crazy. The textbook for this course is Advanced Engineering Mathematics, the 8th edition, Chapter 6 and Chapter 7. This has been a book that has been traditionally used for many years now. And the grading policies are there. The grading policies will be shared with you on the Moodle under the title Basic Information. There are 7 weeks course. Each week has 3 contact hours, 21 hours of class time, and 7 tutorial hours. The tutorials are compulsory. You have to attend it. They'll be handled by PhD students and your BTech students. The teaching will be done by the BTech students. And then if you want help sessions, they'll be conducted by some of the PhD students, etc. We'll give you the information as we go along. Next is a general outline of this course. This course is basically a course on matrices. The emphasis will heavily be on matrices, abstract linear algebra. Linear algebra is a vast subject, and this is the beginning. Abstract linear algebra, dealing with abstract vector spaces, linear transformations, and stuff like that, that will be done in the future courses. But here, linear transformations may only make a brief appearance. Abstract vector spaces will make only brief appearances. The emphasis primarily will be on vector subspaces of Rn and matrices. So matrices will be heavily feature in this course. So you know about matrices from your 12th standard courses. You studied matrices for your JEE preparations. You know what is how to add matrices, how to multiply matrices. Of course, you cannot always multiply 2 matrices. There are some conditions. You can multiply a 2 cross 3 matrix with a 3 cross 4 matrix, etc. And then how to take the transpose of a matrix, how to take the inverse of a matrix, what is an invertible matrix, the determinant of square matrix, and so on. And then how to solve systems of linear equations using matrices. Now, when you have a large number of systems, say you got a system of, say, 10 equations in, say, 16 unknowns, doing it by hand in an ad hoc fashion is not really the most intelligent way to do it. You must have a more streamlined and algorithmic way to go about the job. And this is achieved by Gauss elimination, the Gauss elimination method. Then we'll talk about row echelon forms and elementary row matrices, row reduced echelon form, and Gauss-Jordan method for finding inverses. So this is the summary of the material that will be covered in the first week. So these video clips will be for half-an-hour capsules. So the lectures will be numbered as lecture 1A, 1B, 2A, 2B, 3A, 3B, and so on. And they'll be uploaded in some public domain, and you will have access to it. Okay, so what are matrices? A matrix is basically a rectangular array of real or complex numbers. So in the slide, you see a 2 by 2 matrix. You see a matrix with 2 rows and 2 columns. Sin x minus cos x, sin x. Okay, and this is an example of a square matrix. Here, you may argue that this is not really a matrix of numbers. This is a matrix of functions. Yes, you're right if you say so. matrices, most of the matrices that we'll encounter in this particular course, the entries will be real numbers or complex numbers. In fact, mostly it will be real numbers. Rarely you will see matrices whose entries are complex numbers. And still, and even more, even rarer is occurrences of matrices with functions like sin x minus cos x sin x. So sometimes matrices also have entries as functions. Let me just round up this discussion by giving some examples. Matrices whose entries are functions you have encountered in MA109 and MA111. For example, if you take a function from R3 to R, which is differentiable, now the gradient of the function, grad f, is a row vector, a matrix which has only one row is called a row matrix or a row vector. A matrix which has only one column is called a column vector or a column matrix. So this gradient of f is a 1 cross 3 matrix. This is one row and 3 columns. Del f by del x1, del f by del x2, del f by del x3. Similarly, if you have a function from R3 to R2, so the input, there are 3 input variables x, y, z. There are 2 output variables u and v. So what is the derivative of f? The derivative of f can be displayed as a matrix. Del u by del x, del u by del y, del u by del z, del v by del x, del v by del y, del v by del z. The individual, you simply take the gradient of u, put the gradient of u, underneath you put the gradient of v. Or you may have encountered in your MA10111 Jacobians. So you got u equal to r cos theta, v equal to r sin theta, del u by del r, del u by del theta, del v by del r, del v by del theta. That's a 2 by 2 matrix of functions. In your MA108, you're going to encounter matrices whose entries are functions. So these are some of the examples which are not in the slide. So I thought I could just make a scanned handwritten slide. So that's the example of matrices with functions. Occasionally we'll encounter matrices whose entries are functions, but in this course primarily we'll be looking at matrices whose entries are real numbers, sometimes, rarely, complex numbers. So what is a M cross N matrix? M cross N matrix. Now always the M will refer to the number of rows and N will refer to the number of columns. This is a convention. Okay. This is a convention, and so you got M rows. First row, jth row, and the M and the last row. First row is A11, A12, A13, dot A1n. The jth row is AJ1, AJ2, dot AJK highlighted. Dot AJN. So AJK is the entry in the jth row and the kth column. So when I say AJK, the first subscript J refers to which row the entry belongs, and the second one refers to which column the entry belongs. This is a convention that's going to be used throughout. Please adhere to this convention. Okay. So this is a general example of a matrix, a M cross N matrix, an M cross N matrix. So for example, here you see a 3 cross 1 matrix. Here you see a 3 cross 1 matrix, 3 rows and 1 column. Such a thing is also called a column vector. Whereas in the second example, you see only 1 row, but 4 columns. So it's a so 1 cross 4, number of rows. The first piece of data will be the number of rows. The second piece of data will be the number of columns. This is a 1 cross 4 matrix. Okay. So for example, let us just scroll through. Here you see a 2 cross 3 matrix, and this is a 3 cross 2 matrix, for example. So you got lots of examples of matrices here. Okay. This is another example of a 3 cross 2 matrix. That's a 2 cross 2 matrix. Okay, so now that we have seen all these examples, let's go back to the slides. So you got, now you know what is a matrix, what is the jkth entry of a matrix, what is the size of the matrix, the rows of a matrix, the columns of a matrix which has only 1 row, a row vector, a matrix which has only 1 column, that's column vector. So when are 2 matrices equal? When are 2 complex numbers equal? 2 complex numbers alpha plus I beta. and A plus IB. Suppose A plus IB and alpha plus I beta, where A, B, alpha, beta are real. When are two complex numbers equal? When the real parts are equal and the imaginary parts are equal. The individual pieces are equal. Similarly, when are two matrices equal? Two matrices are equal when the corresponding entries are equal. So you have the notion of equality of a matrix. And then you have the identity matrix. What is an identity matrix? What is a square matrix? A matrix is a square matrix if the number of rows or the number of columns are the same. M cross M, N equal to M. Such a matrix is called a square matrix. The very first example here is a square matrix. Okay. So what is a zero matrix? If all entries are zero, then you call it a zero matrix. That's a zero matrix. What is the identity matrix? An identity matrix is a matrix which has ones along the diagonal and the off diagonal entries are zero. So what is a 3 cross? So there's an identity matrix is a square matrix. Zero matrix can be any rectangular matrix can be zero. All entries are zero. That's a zero matrix. So you can have a zero matrix of size 2 by 5. You can have 2 rows and 5 columns, but all the entries are zero. But identity matrices are all square. You can talk about a 2 by 2 identity matrix, a 3 by 3 identity matrix, a 4 by 4 identity matrix, etc. So what's a 2 by 2 identity matrix? 1 0 0 1. 2 by 2 identity matrix is 1 0 0 1. So suppose I put x equal to pi by 2. Suppose I put x equal to pi by 2. I get 1 0 0 1. It's a 2 by 2 identity matrix. What's a 3 by 3 identity matrix? 1 0 0 0 1 0 0 0 1, etc. You get the general idea. So you got the notion of a zero matrix, the identity matrix. Identity matrix only for square matrices. Zero matrix can be any size. Transpose of a matrix. What is the transpose of a matrix? You simply, loosely speaking, the rows and the rows become columns, columns become rows. It's best to look at an example. Look at A and look at A. What are the rows? 5 minus 8 1. The first row of A becomes the first column of A transpose. The second row of A becomes the second column of A transpose. That's the idea of transposing. Just make convert the first row into the first column, convert the second row into the second column, and so on. That's the idea of a transpose of a matrix. Now, if I take the transpose of a transpose, what's the transpose of this? The first row has to become the first column. So 5 4 is the first row, that has to become the first column, 5 4. So if you take A transpose, obviously you're going to get back A. So transposition, a transposition takes an M cross N matrix and gives you a N cross M matrix. It coughs out an N cross M matrix. Symmetry. A matrix is a square matrix if the number of rows and number of columns are equal. Okay. A matrix is symmetric if A equal to A transpose. Now, what is the size of A? It's an M cross N matrix. What is the size of A transpose? It's an N cross M matrix. So if you want A to be equal to A transpose, and compulsorily M must be equal to N. Okay. So symmetric, such matrices are called symmetric matrices. So symmetric matrices are square matrices with the property that A equal to A transpose. A matrix is skew symmetric if A equal to minus A transpose. Okay, so you got the notion of symmetric matrices and skew symmetric matrices. Is the identity matrix symmetric? Is a 3 cross 3 identity matrix symmetric? Yes. Is a 3 cross 3 zero matrix symmetric? Yes. So zero matrix, a square matrix, all of whose entries are zero, is obviously a symmetric matrix. And the identity matrix, a 3 cross 3 identity matrix, is also a symmetric matrix. Symmetric matrices will feature very importantly in the last part of this course. Adding two matrices. Now you can only add matrices which are of the same size. You can add a 2 cross 3 matrix to another 2 cross 3 matrix. You can't add a 2 cross 3 matrix and a 3 cross 2 matrix. You can't add them. So A equal to AJK, B equal to BJK are two matrices, generally rectangular matrices of size M cross N. Then the sum of the matrix is simply take the corresponding entries and simply add them. What is the 1 1 entry of the sum? you simply take the individual 1 1 entries of the individual matrices. A11, B11. Add them up. You get the 1 1 entry of A plus B. That's all that there is to it. Scalar multiplication. Multiply all the entries of the matrix by a fixed number lambda, and that will be the lambda A. So lambda A is simply lambda of AJK. So you got addition of matrices and multiplying a matrix by a real number or a complex number. Scale. More generally, now you have to do matrix multiplication. So how do you multiply matrices? Before you multiply matrices, let us ask how to multiply. Let us pretend that the left-hand side matrix has only one row. Let us pretend that the left-hand side matrices have only one row. In fact, let us take A1. Let us take J equal to 1. A11, A12, A1n. And let us pretend that the right-hand side matrix has only one column. Only one row has been displayed. Only one column has been displayed. Basically, in this slide. So how do you multiply these two things? One way to multiply this is to think of the dot product. Suppose n is 3. Let us assume n is 3. So A11, A12, A13. So just three numbers. A11, A12, A13. And then B11, B21, B31. So it's a three entry row matrix and a 3 entry column matrix. A row with 3 entries and a column with 3 entries. How would you multiply? You may want to think of the dot product. You may want to think of the dot product, or you could do it even with you can have a row matrix with 2 entries and a column matrix with 2 entries, or you can take a row matrix with 5 entries and a column matrix again with 5 entries. The number should be the same. The same n here and the same n here. It's a 1 cross n and an n cross 1. And the result is a real number. The dot product, as it is called, as you might want to call it. You take the first entry here and first entry here and multiply them. Take the second entry here and second entry and multiply them. Last entry here and last entry there and multiply them, and add all the things you get. So that's how we'll multiply a row by a column. Okay, now that you know how to multiply a row with a column, the rest is very simple. You take a matrix A with m rows, and you take a matrix B with certain number of columns, with p columns. M rows and n columns. B has n rows and p columns. The second n here should be the first n over there. Then A into B is meaningful. Here the matrix product is A, B. I don't like this multiplication symbol. I would like to call it C equal to AB. C equal to AB. The A times this multiplication symbol should be replaced by, but it should not be there. It should be suppressed. C equal to A into B. AB. Just put the two letters together. That's all. That's the standard notation. So what are the entries? So what is the IK? What is the JLth entry? What is the entry in the Jth row and the Lth column? Do the following. Take the Jth row of A. Take the Jth row of A and take the Lth column of B. The Jth row of A is what is displayed here, and the Lth column of B. So, but you know how to multiply a row by a column, right? Just now we have seen that. And that's a real number or a complex number. And that whatever you get, whatever real number you get or whatever complex number you get is your CJ. That's how you multiply matrices. And matrix multiplication has many features in common with multiplication of numbers. Some features don't go through, of course, we will see that. What are the features? What are the pleasant features of matrix multiplication? Suppose, for example, A is an n cross n matrix. I want to multiply it with a B. The B must be n cross P. The second number here should be the same as the first number for the second one. So A is n cross n, B is n cross P. The product AB is, what is the size? M cross P. Now I want to multiply the product AB with yet another matrix C. So the matrix C must have P rows and say Q columns. So AB parenthesis C will be a matrix of size M cross Q. That's the right hand side. On the other hand, I could first multiply B and C. If I multiply B and C, B is a N cross P matrix and C is a P cross Q matrix. BC is a N cross Q matrix. That's an N cross Q matrix. And A is a M cross N matrix. So A times BC is a M cross Q matrix. So first of all, at least size A times BC and AB times C, these two matrices at least have the same size. Okay, thank you very much. Not only they have the same size, these matrices are equal. In other words, matrix multiplication is associative. This is a very pleasant feature of matrix multiplication. Matrix multiplication is associative. Okay, the associativity is easy to check. We leave it as an exercise. Okay, now we have two operations, or rather we have several operations on matrices. One is you take a matrix and you take its transpose. Or I could take two matrices and I could of the same size and I could add them up. Or I could take two matrices of sizes M cross N and N cross P and I can multiply AB. AB is a M cross P. So now there are three different operations. What is the relationship between these operations? For example, you can ask, is matrix multiplication, what are the properties of multiplication and addition of real numbers? Multiplication distributes over addition. Is the distributivity law true? That's an important question. Another question is that you could take two matrices A and B, say of the same size. A is M cross N, B is also of M cross N. Then I have A plus B. And I can say A plus B transpose. Is A plus B transpose the same as A transpose plus B transpose? Yes. Answer is yes. A plus B transpose is A transpose plus B transpose. You would have guessed it. It is absolutely trivial. But what is more interesting is the next theorem. Suppose I take two matrices. What is the relationship between transposition and multiplication? I have taken A is M cross N and B is N cross P, and I can form the product AB. Now I form the product AB and I take the transpose of the product. Is the transpose going to be A transpose B transpose? No. Because what is the size of A transpose? M cross N. What is the size of the B transpose? P cross N. Can I multiply A transpose and B transpose? No. I can multiply B transpose and A transpose. That product, the product of B transpose followed by A transpose, that is meaningful. And not only is AB transpose meaningful, B transpose A transpose is meaningful. A transpose B transpose is not meaningful. So what you can do is you can compute AB and take the transpose. You can compute B transpose, A transpose, and their sizes are such that you can multiply them. You can calculate B transpose, A transpose. The two results are equal. AB transpose is B transpose, A transpose. Again, the proof is routine and you can check it by yourself. All right. So now A is a 3 cross 2 matrix and B is a 2 cross 2 matrix. 3 cross 2 multiplied by 2 cross 2. 3 into 2, 2 into 2. The product AB makes sense. But the product BA doesn't even make sense. BA, you cannot multiply, you cannot compute BA. You can compute AB. A transpose is a 2 by 3 matrix. B transpose is a 2 by 2 matrix. So B transpose A transpose, you can compute. Correct? So here in this exercise, there is a little trap for you. Compute A transpose, B transpose, compute AB. Can you multiply AB? Yes. First row, first column. R1, C1. R1, C2. R2C1, R2C2, R3C1, R3C2. AB can be calculated. Is he asking you to calculate BA? No. You can calculate A trans. He's asking you to calculate AB. He's asking you to calculate AB transpose. And he's asking you to calculate B transpose A transpose. As per the previous theorem, AB transpose must be B transpose A transpose. And now he's laying a trap for you. A transpose B transpose. You can't compute. What is the answer? A transpose B transpose doesn't exist. That is the answer. Compute these things. So you can actually calculate this, calculate this, calculate this, calculate this, calculate this, and then for the last one you have to say it doesn't exist. Okay. The dot product as a matrix product. We already discussed this. If I take two, okay, if I told you can take a row vector and a column vector of the same size. And so what happens is that the dot product of now here you have two columns. If I can't multiply them as matrices, I can't multiply them as matrices. So in order to multiply them, what do I have to do? I have to take I want to multiply these matrices to get a real number. And I want to call it the dot product, the scalar product, no? Inner product. Dot product of two vectors in R3 is a scalar. V1, V2, V3, W1, W2, W3. But vectors will conventionally be written as columns. Vectors will conventionally be written as columns, but I want to compute the dot product of two vectors. I can't do it right away. I'll have to convert one of the columns into a row and then do the matrix multiplication. So the V dot W is by definition. V dot W is by, this is a definition. V dot W is by definition. Convert it into a row, V transpose W. Okay. What will happen? What will happen if I calculate W transpose V? W transpose V will be W dot V. What is the size of V transpose W? V transpose W is a 1 cross 1 matrix. What is W transpose V? Again a 1 cross 1 matrix. What is the transpose of a 1 cross 1 matrix? If I take a 1 cross 1 matrix, 1 cross 1 matrix is its own transpose. Isn't that so? A 1 cross 1 matrix is its own transpose. So V transpose W is a 1 cross 1 matrix and I take its transpose. But when I take its transpose using the basic rule, I get W transpose V. But I know that they're equal because they're both 1 cross 1 matrices. So V transpose W equal to W transpose V. In other words, the dot product is commutative. The dot product of two vectors is commutative. What about VW transpose? V is a column vector. W is also a column vector. What is W transpose? What's the size of W transpose? Size of W transpose is a 1 cross n matrix. So V is a n cross 1 and W is a 1 cross n. So VW transpose is a W is a 1 cross n. V is a n cross 1. So what's the size of VW transpose? Size of VW transpose is an n cross n matrix. Please calculate VW transpose. VW transpose is a n by n times n matrix. It's a square matrix with n rows and n columns. Is this also the dot product? Answer is a no, because the dot product is supposed to be a scalar. The dot product is supposed to be a real number. Whereas VW transpose is a matrix with n rows and n columns. So it will not be a dot product. It's quite different. Okay, so let us take a pause, and this completes lecture 1A. We'll take a pause and we'll resume lecture 1B. Thank you.